One of the ideas is something called radial density, and basically the idea is if you've got the middle of a city, lots of people might live there, and as you move away from the middle of the city, there might be less people living there, or the density might change. You might have not many people in the middle and more people when you get to some suburbs, and then less people. And you can imagine that you could have some sort of function that describes, well, okay, I know where the center is, and as I move out, this is how the population density is affected. And then you could ask a question like, well, from the city center, maybe, like 5 kilometers to 10 kilometers away, in this band, how many people live there? And that's exactly what radial density and population can combine together to do, along with integration, because integration is great at finding areas. So let's just get rid of that for a second. Hopefully you've got the basic idea, and we're going to start with a bit of a formula. Formula is the population within a certain radius, r, is given by this formula. The population is 2 pi of, you need to know the inner radius and the outer radius as I had drawn. So you got your city center and you've got an outer and an inner radius, a lower and an upper bound. So this is that upper bound and this is that lower bound, just like we've seen in integration. And then you have to multiply that by r times p of r. This isn't actually p of r. This is a special new thing called rho. It looks like the letter P, or it can look like a symbol like that. That's the Greek letter rho, and it means density. So this is your density function right here. And you'll notice that you're multiplying the radius and you're also multiplying a density function that depends on how far away you are. It depends on the radius. So this whole integral is with respect to r. And let's just define some of the other parts of it, that being where this whole r is usually centered at the middle of a city. So we'll take a look at an example, and these aren't real numbers, but we might need that equation. Let's take a look at an example around the city of Calgary. Okay, so the population of Calgary has a radial density function. This radial density function will always be given to you. And there it is, the density function is equal to 10 times 2 plus r squared to the power of negative 1/2, and r is the radius from the city center in kilometers, and rho is in thousands of people per square kilometer. How many people live in that ring, as I was saying, in this ring, between 5 and 25 kilometers from city center. So we use the formula P is equal to, and we go from 5 to 25, and it's R times this density function, 2 plus r squared to the negative 1/2. And to calculate this, we can't take this integral without using substitution. So the substitution that we're going to want to use is we want to simplify that 2 plus r squared, and du becomes 2r dr, or dr is du over 2r. And when you substitute that in, you get the integral from, and then this becomes 10 times u to the negative 1/2. All of this, sorry, u to the negative 1/2. Sorry, as always, I made a tiny mistake. This is not supposed to be a bracket around this piece or this piece. It's 10 times, it's only 2 plus r squared that's raised to the negative 1/2 if I look very carefully back to here. So I get r times 10, or 10r. And I did also forget the 2 pi in front, so here there should have been a 2 pi, and here there is a 2 pi. That's because it's a circle. That's part of the formula that you need to know. And I need to make sure that I change these limits of integration, because these are r values, and now I'm going to start dealing with u values. I also forgot the dr, not doing well today. And this dr is now du over 2r. So some stuff cancels, r's. Some stuff needs to get changed. U's are now 2 plus r squared. So I have to take the r, square it, that's 25, and add 2. The r, square it, that's a pretty big value. 625 plus 2 more is 627. And I can see that I've got a 10 and I've got it divided by 2. If I deal with both of those, I think I get some cancellation happening out, and I end up getting an integral of 10 pi, evaluated from 27 to 627, of u to the negative 1/2 du. Applying integration rules, I calculate that out as 10 pi times u to the positive 1/2 divided by 1/2, evaluated from those two numbers, and I get a population of about 1247. But don't forget that this is in thousands. So that really translates to a population of about 1,246,823 people. Don't count the part people. Another application that's super similar to this is something called flow rate. And flow rate is, if you imagine a tube and water coming through the tube, you would need to know the radius of the tube, and you would need to know basically like density. How fast is what's the velocity of the water going through at different parts of that tube? And then you could calculate the total amount of flow through that. And they use this for engineering, for pipes and things like that. They also use it in medicine for the amount of blood going through capillaries and things like that. And there's a formula for it, and you'll notice it looks really similar. Of course, you go from 0 to r because you don't have the ring idea happening. You have a flow from the middle just to the outside, but you still have a radius, and you have v of r, and this is the velocity function at radius r. And then, of course, it's dr. One last thing that we can do in this section has to do with average value of area. So let's take a look at that as the last part. So integral areas can also have a mean or an average value to them. To see how the formula is generated, we're going to go back to taking a look at how we found just areas, and one of the ways that we did that was using r sub n, which is adding up all those rectangles. So you've got the base of the rectangle times the function evaluated at the first point and the function evaluated at the next point, all the way up to the function evaluated at the last right endpoint. And we also saw that the change in x is always b minus a over n. So this formula becomes b minus a over n times all of this stuff. And the definition of average is, well, you get a bunch of numbers, you add them all up, and then you divide it by however many numbers you have. Well, I've got a bunch of numbers, add it all up, and I'm dividing by how many numbers I have. So these two parts of this equation really are calculating the average. So if I get rid of this b minus a, and the easiest way to get rid of it is just divide both sides of this equation by b minus a, I get an equation that looks like r sub n gets divided by b minus a, and I end up with an average value of all of these x values added up divided by n. And that's then taken the limit of that to find the entire area. So when you go to area, you're then dealing with the limit as n goes to infinity of r sub n. But now when you're dealing with this average idea, you want to find this calculation instead. You want to have your r sub n. So when you do the limit of r sub n, you're getting an integral now from a to b of f of x dx. So that's this piece. And then if you want to calculate the average, the only part that you don't have when you take the limit is this 1 over b minus a. And so if you ever want to calculate the average or mean value of an area, you can use the integral from a to b of f of x dx and multiply it by 1 over b minus a. There's a great example in the online book in section 6.2.4. It's example 8. It's about a monkey jumping. And basically you're finding, well, if it's got an initial velocity and the velocity changes at this rate, what is the average velocity of this jumping monkey? It's actually a pretty cool little example. There's an extension to this as well that talks about the mean value theorem and how it applies to the mean value theorem of area, that there must be some place where there's the average area underneath the graph, which makes sense once you understand the mean value theorem and can apply it to integration as well. I don't have a ton of time to get to that, so take a look at the textbook as well for this section. I know it's a pretty heavy-duty section, but you might need to spend just a little bit more time reviewing it. Okay, we'll see you in class.